So today we're going to cover this Soviet era Nixie module with the IN-14 tubes in it. They come in a big gang. They are modular, so you can add or subtract to your end amount that you're going to need for whatever it is that these were for, or maybe you have a project coming up. So today's video we're going to talk about how to do that, how to get these up and running, reverse engineer them so you can understand a little bit more and get them fired up to do the count. We will not talk about why this 7 isn't working, although I think there's a defect in the tube. But that aside, this is up and running the way it should be, minus the 7 of course. Bad tube, just my luck of the draw. That's why I don't play the lottery. I have all those other ones to hook up, and this is the one I get. So let's talk about our little setup real quick here. I have a 7490, some little jig I made up a while back just to get a binary coded decimal output. Anytime I needed a binary coded decimal, we can get it from this device here. So all it is 5-volt power supply going in with a 555 timer, and that clocks the 7490, and you can see the 4 LEDs representing the binary coded decimal, the 8421, with the 1 being on the right side. You can see it counting. It counts to 10 and resets to 0, or counts to 9 and resets to 0 for 8 count of 10. So let's talk about what we have going on here. Now, as I said, these modules come apart, and we have one apart here, and we're going to leave it counting for a moment, and then we'll shut it down at some point. You get something in like this, and you have all these pins on the back, and it looks overwhelming. Like, what do you do to get these working? So you break into it and just try and understand by looking at the components inside what's going on there. So we'll get to that in a minute. But these modular units, voltmeters, frequency counters, using this technology at the time, this is like 70s era technology. They might have used it into the 80s a little bit. Apparently the Soviets date code on this is 1991, so it's very interesting how that carried out longer over there. Generally frequency counters and voltmeters and anything similar that uses display logic, I drew up a little block diagram here. So you can cascade a bunch of displays, and they're all set up pretty much the same way. And it starts with one clock signal, and you have decade counters. Alright, these count 0 to 9. And when this hits 9, it sends a carry pulse to the next one. And when that hits 9, a carry pulse to the next one. So on and so forth, for however many digits you're going to have. These output 4 lines of BCD, the 8421. Okay? And that counts 0 to 9. I'm not going to go over a binary coded decimal tutorial in this video, but there's plenty of the information on how to count in binary. If you don't know, check out a few other videos on that and come back. So that BCD from the counter could either go to a driver decoder directly, or in a scenario where you need to do measured timing intervals, you might want to latch or have a storage device to hold the display in between timing measured intervals. You would use a device called a storage device, or a latch. Okay, and that gets a signal, which I did not represent here, to enable the latch. You either high or low signal, and that would then correct directly across all the latches, all the way across, that you cascade together, all on the same line. So that would either hold the display or hold the data, because I'm not talking to the display directly, but hold the data and or let it pass. Alright, depending on what the enable line is doing. So your driver decoder then takes the binary coded decimal and converts that to something your display wants to see. So you would match your decoder to whatever display you're using. If you got a Nixie tube, it would take a high voltage 1 of 10 driving type decoder. If you had an LED 7 segment display, it would take a different type of a decoder. Sometimes the latches are intertwined or integrated in the display or the decoder, depending on the technology used, especially this day and age where everything is integrated. That, in a nutshell, having that understanding how these are configured now brings you to maybe understanding a little bit more of what's going on in this device here. So this is my BCD generator, as we discussed before, and we're going to now move into how I decided what pin on what did what in here, not having any knowledge other than basic understanding of operation. So what we're going to do, we're going to turn off the power supplies, shut this down, because I got a 170 volt supply back here, so I don't want any stings tonight. Excuse my reach. Okay, so we're now shut down. I'm going to take some of these things, just move them aside so we can talk about our main device here. And we'll zoom in a little bit on this so we can see what's going on here. Okay, so I open it up and right away I can see we have our Nixie tube, and you can see each cathode is wired to points on the board, and just looking at this quick you can pretty much discern that this guy here is probably your driving IC. And knowing how Nixies work, you got to bring all the cathodes to ground. Then immediately you see this resistor over here that pretty much hones you in, and that's probably the anode resistor. So you're going to have 170 volts probably wanting to feed this resistor, so you can chase that back with your continuity checker. And I did that. I also notice we have this square device here, a little different in the Soviet world. We typically see ceramic capacitors as round discs. I've seen theirs, they all seem to have square ones like this one here. At any rate, TTL Logic generally has a disc capacitor across the power supply, so you know you have your power supplies on each side of this capacitor for your 5 volt logic. You just have to figure out which one is which. Alright, we'll get to that in a minute, how you can decide which is positive, which is your negative rail. Now this device you can look at quickly and probably assume it's a counter, like we discussed in our block diagram, right? You need a counter to be able to send BCD to the decoder. Well, looking at it closer, both packages in this case have Cyrillic writing on them, being from Soviet origin. That becomes a little tricky then for us over here in USA to wrap our head around that. Us Nixie nuts, if you will, we pretty much all know that the 74-141 Nixie driver, I guess Texas Instruments probably came out with that, or one of the big names. But anyway, it is pin compatible to the Soviet version. So I started thinking, well, let's start looking up the part numbers on this, and maybe there's a pin compatible TTL device over here. So I actually used eBay to figure that out, and I'll give you the part numbers in a minute, but I put it's K155 TM5, even though some of those characters are acrylic. I put them into an eBay search because Google didn't really help, and it came up, and the correlation in a active listing actually said it was the same as a 7477. So 7477 is a latch storage device. So I started digging more on that to try and find out, pin out information and stuff, but knowing nothing, dead ends on the Soviet data sheets, and if I did find, I wouldn't be able to read it anyway. I started putting in the 74 series part numbers and looking for data sheets, and data sheet for the 74-141 and the data sheet for the 7477, and I actually was able to come up with information I needed to get pinouts. Once you have the pinouts, then you can figure out where your power supply rails are, all your outputs, your inputs, and then you can kind of map it out, and from there start taking notes and work your way backwards and figure out where you need to apply your binary coded decimal, your negative rail, your positive rail, your 170 volts for the Nixie anode resistor, and the carry or the enable line for the latch as well. So I did all that. This here is the acrylic version of the Nixie driver 74141. That's over here, right? And here's our anode resistor. I measured that 27K, so that's pretty standard for applying 170 volts to. Our capacitor, okay, and then this guy, the K155 TM5, which is pin compatible with the 7477. So once I started laying this out, then you can start filling in what your pinouts are from the data sheets. Your +5, your 0 volts here, the 0 through 9 outputs for your Nixie device, but then you have your 4 lines of binary coded decimal that needs to feed this device here. So I bring these actually come from the 7477 latch, okay, and they're represented as Q. The outputs on this device are represented as Q, so 1Q, 2Q, 3Q, 4Q. The inputs are represented as D. Okay, so 1D, 2D, 3D, 4D. Alright, and it doesn't really matter as long as you have the 1 to the 1, the 2 to the 2, the 3 to the 3, the 4 to the 4. That's your data in, data out. And all you have to do is hit the enable line, which is the C. They have the 1C, 2C, 3C, 4C, and those you're actually going to bind those together, join those together electrically, and that's your point at which you apply your high or low signal for the data to pass or to be stored in this device. Okay, so and then working backward from there, we get over to our connector. Okay, now if you start trying to lay out this connector, if you have these same modules, I have it laid out as it is on the counter here on the desk, alright, the way it lays out, but when you flip this back up in the module, this bottom becomes top, so it gets a little backwards and upside down. So I did note that this is actually when installed in a module, this is the top of the unit. So if you start working off of this pin out here, be aware of that. It'll be upside down and backwards pretty quick. This is the IC side of the board. In other words, we're looking at the end of this, but really it's laid like that. So you see the blue side here? This is the IC or blue side. The other side is the solder side. So there's actually 2 rows of pins. You have to get on the right row. So the 170 one is at the one end here, and there's actually pin numbers on each side of this connector. If you look on the end, there's a 2 and a 23. I have them represented here, 2, 23. Okay, so on the 2 end, here's your 170 volts comes in there. These 2 pins are electrically joined. Okay, jump down 1, 2, 3, 4. Okay, these 2 are electrically joined. They're your plus 5 volt rail. The next one over, electrically joined. That's your enable. Okay, we'll get to the enable signal in the end. We'll discuss how that works. Okay, now the low side or the ground is only on one side. If you solder over here or connect over here, you're not going to get it. You have to go to the other side, which is the bottom row, in this case over here. That's apply your ground or 0 volts there. The 170, the ground for the 170 volts gets joined in, commoned up at the same point here for reference. Alright, so your plus 5 and your plus 170 share that same 0 volt point. Now inputs, BCD inputs come in here. A on one side, B on the other, C on this side, D on the other. Okay. There are also decimal points in this Nixie tube, which get run directly, not through any drivers or latch or anything. I did call that out here, although we're not using them, we're not lighting them up, and they're up here too, a decimal point DP, right? So if you want to do something with decimal points on these modules, you can as well. So I hope this arrangement and diagram helps you in understanding how this wires up. We're going to explain next the 7475, which is not here, is also a latch storage device in the same series of ICs, but the 7477 has the same signal for the enable, and we're going to talk about that. So right from the data sheet, it pretty much spells it out. Data at the D input is transferred to the Q outputs. So D on this side, Q on this side. Okay, data is transferred from D to Q when the enable C is high. So your C enable over here, we have that out here. You really don't have to worry about connecting anything here because it's all on this connector. So find that enable line, and if you make that high, okay, that's going to allow the data to go through the latch and pass to your Nixie driver. Your Nixie will count. Okay, leaving it unconnected will work because that technically is a high, but leaving floating inputs on TTL is not recommended. But for simplicity of just firing up for the first time, if you leave it disconnected, it will count. When you bring the enable line on C down to low, in other words ground, the data present at the time that goes low remains at the D inputs. Well, no. Let's clear that up. So when the enable line goes low, the data present at the time on the D inputs, that will be retained at the Q outputs. Okay? So basically, when C goes low, whatever's on D at the time C goes low, Q remains what it was on D. and will stay there until you bring the C enable line back high again. Okay, so that's how the latch works. Any questions on that, you can always put something in the comments. I'm just trying to run through this quick to keep the video at a moderate length. Binary coded decimal we discussed. If you have any questions on that, look up some videos how binary decimal works. But basically 8421 is the layout, DCBA, and that's the same DCBA you see on the Nixie driver here. Okay, that's how that's usually called out on data sheets. So that's pretty much it. With that said, if you want to do something with these, you need a string of counters, okay, because there's no counting device to generate your BCD. But so either you get a string of counters that form binary coded decimal, and that gets tricky because if you're going to make a clock, some of them have to count to 6, some of them have to count, if you want a 24-hour clock, you need a 24-hour section, and it gets, I've done those videos because I've made a lot of clocks doing that, but there is an easier way, and if you want to just do a 6-digit clock, you can put 6 of these modules together. There is a neat, they sell it on eBay as well as their own website, neonnixie.com, which will bring you to allspectrum.com. It's All Spectrum Electronics sells this IC, and you might have seen this listed before. Neon 6-digit. They have a 4-digit one as well. We like our 6-digit clocks, right? So Neon 6-digit Nixie clock controller. Here's your schematic. This is online. Look it up on eBay. You might find it. But neonnixie.com brings you to allspectrum.com. This chip is really cool because it has 6 separate outputs of binary coded decimal. So you could feed the binary coded decimal to these modules. You bring in 4 lines of BCD here, 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 and okay, add 2 more digits and 2 more sets of BCD, and you got a 6-digit clock, right? So very simple to implement this one because I've done it. It's really neat, and you can do 2 different time bases. You can use a watch crystal, they give you that option, or the Dallas DS32 kilohertz guy here, right, and a super cap backup, and you get all these parts right from allspectrum.com. Check them out. I think that's going to be, if Peter, if you're watching this, or even Matt knows about this already, but Peter, if you want to do something with these Nixie modules, that all spectrum Nixie controller may be the way to go. And then just feed your binary coded decimal into each module from each set of outputs on this IC, right? So I will leave a link in the description to get you steered in the right direction to investigate this option, and maybe you have another option. I don't know how microcontrollers work. You know, they generally set up multiplexing and stuff. If you got a multiplex, you're gonna have to reconfigure everything on these. Maybe there's enough I/O pins on a microcontroller or not for 6 sets of binary coded decimal to feed all these. I don't know, but at any rate, I'll just finish up with a close-up on what's in here, and leave you with that. So I hope I took some of the mystery out of this device, as well as gave you hints as to figuring out other devices, and basically look to see what's in there. Your logic family. Have a little basic understanding also helps. And then just work it backwards, and you can get something like this up and running. So for the couple buddies I have out there to have these modules, I hope this helps you, and anyone else watching, I hope it was a real quick and dirty educational experience from somebody who's not a teacher. I just play one on YouTube. Right? Alright, enjoy your day or evening or wherever you are, and talk soon. Bye.